There we go. All right. So we're looking at number 6. We're going to finish up this homework packet, and you guys can turn this in today. What CP was this? I don't even remember. 26? Okay. 26 or 27? I don't know. Something like that. So this is the last problem, and it's quite cool. I think you'll be ooh and ahhing. It's pretty neat. Okay, a ball is suspended by a piece of string above the floor. The ball swings side to side as if it were a pendulum and maintains a periodic motion for a small length of time. Now, I don't know if you've seen those little desk things where they the balls clack back and forth. Have you seen those? Yeah. I love those things. But they don't last forever, right? Eventually it dampens itself and then goes back to nothing. But we're going to assume for a small length of time, this maintains this periodic motion back and forth pretty good for a while. While the ball is swinging with this periodic motion, students were able to take the following information. The height of the ball above the ground at its equilibrium point was 0.33 feet. So this is a picture of the ball. This is the ground, and here is that little ball on the string. And that is the equilibrium point. The height of the ball at its highest point was 1.7 feet. The horizontal distance from the equilibrium point horizontally to the highest position was 2.26. So this is the horizontal distance was 2.26 feet. The length of time for 5 complete swing cycles was 4.8 seconds. A swing cycle is completed when the ball returns to the same position, like the equilibrium point, and is headed in the same direction. So for the purposes of this, one cycle is the ball starting here at the equilibrium point, and it moves to the right, and then back to the left, and then moves to the right. And then you can see it be continuing in that same direction. So equilibrium right, equilibrium left, and back to equilibrium is 1 second. Okay. We want to label these ordered pairs. The x-axis represents the horizontal position of the ball from the equilibrium point, and the y-axis represents the vertical position of the ball. Position, above the ground. And so here we are 0 feet above the ground. So at equilibrium, what would this ordered pair be where this ball is resting?
0,
0 and then 0.33. Very good. So it was 0.33 feet above the ground. The height of the ball was 0.33 feet above the ground. Okay. And then the ball moves up a little bit, and we get this right maxima over here. What is that? What's 1.7, the x or the y? The y is 1.7. You divided this by 2. Yeah, okay. The horizontal distance from the equilibrium point, it's going 2.26 horizontally from the equilibrium point. So it is literally 2.26.
I read that.
Yeah, you read that weird? Yeah. You thought the spread was 2.26. Yeah, no. From equilibrium to that maxima is 2.26. All right, so then to go back to the left side, the left maxima here, what would that ordered pair be?
Negative 2.26.
Good, negative 2.26 and 1.7. Excellent. Okay, so this is the right maxima, and this is the left maxima, just so we can keep things straight, maybe. Very good. So sometimes it's hard to think like this, but I liked this figure. So now what we're going to do is we're going to model the horizontal position at any time t. So we're using t for our variable now, time, not x's and y's, which is kind of interesting because we're modeling the horizontal position of the ball vertically. Is that weird to you? It's a little bit weird, right? And then over here we're talking about time. Time is passing. Okay, so it's a little bit weird to do this the first time, but let's think about this. So Think about one full swing cycle of the ball. Equilibrium, move right, equilibrium, move left, and back to equilibrium. Using the data above, how long will it take the ball to complete one swing cycle? How'd you get 0.96? Okay, yeah, so it said 5 swing cycles was 4.8 seconds. So if we want one cycle, that time per one cycle, we would do 4.8 divided by 5, and that gives us 0.96 seconds per one swing cycle. Oh, you can't see that, sorry. 4.8 divided by 5 would give us 0.96 seconds per swing. So that means it's completing one complete cycle in 0.96 seconds. So if I'm imagining that I'm starting time at 0, and we're going to do one swing cycle, we would finish that swing cycle in 0.96 seconds. So just like we were doing when we were graphing before, 0.96 seconds, I want to find those halfway points. What's halfway between 0 and 0.96?
0.48.
48, good. 0.48, all right. And what's halfway between 0 and 0.48?
24.
Good, 0.24. And then between 48 and 96?
72.
72, good. Sorry about that.
It was
I keep thinking about the conversation, but there's nothing that I don't want back.
All right. So now that we've got that all broken down horizontally, that's for time, I won't say horizontally, on the time axis, we want to think about that position of the ball. So remember, the swing cycle is equilibrium, move right, equilibrium, move left, and equilibrium. And we're only interested in the horizontal position of the ball. So horizontally, where are we? Right at the very starting place.
Equilibrium.
At equilibrium, which has a horizontal position of 0. So right at 0, horizontally speaking. Then it's going to move over here to the right. Where is it horizontally? 2.26. 2.26 units. So that's the next movement there. It's 2.26. And then it moves back to equilibrium. Where is it? 0. Then it's going to move left. Where is it horizontally?
Negative 2.
Negative 2.26.
So it's the what's that one called?
And then it moves back to equilibrium, where it's back to 0, horizontally speaking. So this is a sine curve. It's kind of interesting. Now that we have a picture, I'm sorry, I couldn't go past what? Oh, sure. I mean, okay, I just drew arrows. That's not. All right, so very good. So now what we want to do is write our equation in terms of t. What is the vertical shift here? Midline, yeah, is 0. Good. You can see that pretty easily. So what's the amplitude?
2.26.
2.26. Good. Ooh, period. What's the period? The period is 0.96 seconds. It starts at 0 and ends at 0.96, so that would be 0.96 seconds. We can use that to help us find b. How do we find b? 2 pi over the period, and so that's going to be 2 pi divided by 0.96. Sorry. And normally, again, I would say you want to simplify that, but we're not going to do that because it's not the point of this exercise. And so I can write a little sine equation. A sine bx. It's starting at 0, so I don't have a c variable here. C plus d. So my amplitude is going to remain positive. So 2.26 times the sine of b, which is 2 pi. I'm going to stick my T on top, using T, not X's. There's no C, and the D is 0, so I don't really need that. I am going to check this really quickly. You do not have to check with me right now, but we'll just do this together so you can see 2.26 sine of 2 pi, whoops, that's not pi, 2 pi x divided by 0.96. There's no C, and the D is 0. I'm going to set my window to go from 0 to 0.96 and negative 2.26 to positive 2.26. And so we can see, there it is. Pretty good? Pretty good. All right. So that clearly models our horizontal position of the ball in terms of time. Okay, you with me so far? You good? Good? Good-ish? Okay, let's try another. All right, so now we want to model the vertical position at any time t. So again, we have time on this horizontal axis. And now on the vertical axis, we're actually modeling the vertical position, which is good. So again, now we want to think about the height of the ball. How high is it above the ground? How high is the ball above the ground for one full swing cycle? And again, that's equilibrium right, equilibrium left, equilibrium. So once again, assuming we're starting at 0 and we've got one swing cycle in 0.96, let's subdivide that out. So halfway would be 48, half of that, 24, and halfway between those two, 72. Okay, so now let's see what happens. At equilibrium, what was the height of the ball? 0.33. 0.33 feet above the ground. Good. So that is right here at time 0. We're 0.33 feet above the ground. And then we're going to move to the right maxima. How high are we at the right maxima? 1.7 feet above the ground. So next we're here at 1.7. And then we move back to equilibrium. What's our height at equilibrium? 0.33. And then we move to the left maxima. How high are we then? 1.7. And then we go back to equilibrium and we're back to 0.33. Oh, interesting. So what happened this time?
2 periods?
2 periods. Very good. So that's very interesting that now here we have 1 period of our function, just going from 0 to 0.48. So that's kind of interesting. Okay. What's the vertical shift of this function? How do we find it?
0.7
This vertical shift is also known as D. How do you find D? Half of low plus high. Low plus high. 0.33 plus 1.7. 1.015 is what that turns out to be, yes. 1.015 is that vertical shift. Okay. Which makes pretty good sense here. So the midline somewhere between 1.015 seems about right. How do you find the amplitude? High minus D, high minus D. So 1.7 minus 1.015 is what? 0.685 sounds more right.
Did I not say that?
No,
I can't.
Okay. So what's the period of this function?
0.48.
Is that 1 period or 2 periods?
0.48.
0.48. Yes. This period is happening in 48 hundredths of a second. And as opposed to, here we have 2 full periods shown in that amount of time. So we want 1 period, which means what's B going to be? 2 pi over 0.48. Very good. And is this a sine or cosine curve? Cosine curve. That is reflected. Reflected. Good. So the A value should be what? Negative 0.685. Cosine curve that we're looking at, B is 2 pi, I'm going to put my variable there, times t over 0.48. There's no horizontal shift, and we want to add in our midline. Our midline is 1.015. All right, so now again, I'm going to go ahead and just double check this.
Oh, that's.
All right, so I didn't change the window too much, but I can check a point here, and like this point right here is 0.24 and 1.7, so I'm going to use trace and type in 0.24, and I do get 1.7 right at the tippity top, so that looks like a great equation. Okay, so this is the really cool part. Okay, you're going to watch the motion of the ball on your calculator. So what we just did is we created an equation that gives the horizontal position of the ball and an equation that gives the vertical position of the ball. So if you will, in terms of time. And so what our calculators are able to do is if we give two equations, one that gives a horizontal position in terms of time and another that gives a vertical position in terms of time, then it can create an XY ordered pair to paste the ball on a coordinate plane in terms of time. It's very, very cool, and it's called parametric mode. Yeah, so you do have this in your calculators. So in your calculators, we want to put our calculator into parametric mode. On the TI, you're going to go to mode. On the TI, you're going to go to mode. I'm going to zoom out just a little bit here. Okay. That would be par. You can see normally you're in function mode. You're going to need to switch back to function mode. And we want to be in parametric mode. So highlight that. On the Casio, you're going to be in your graphing menu. And we are going to change the type of function that we're doing. So you see type right there. We want to change the type. Again, right there it says parm. That's not Parmesan cheese. It's parametric mode. All right. And so you're going to change that. All right. So TIs, you're going to go back to y equals. And now you see that both of us have sort of different notation. You see x1t and y1t. And same for the Casio, xt1 and yt1. So we have an equation that's going to give the x position, the horizontal position, in terms of time. And so we want to enter our two equations that we just found. Well, we're not doing anything yet. Okay, so x of t, we're going to type in this equation that we found for x of t. So we're going to type in 2.26 sine of 2 pi, where is pi? There it is. And I have my variable on top, so I'm going to use the same t as variable as you normally would. Divided by 0.96. It changes the variable for you. And then same thing here, 2.26 sine of 2 times pi times t divided by 0.96. It automatically puts the t. It uses the proper variable. You just press the same button as you always do for your variable. Okay. 0.96. All right. Are you with me so far?
Not even sort of. I don't know where you put it.
Go to type. Okay, and now you're going to type in. Okay. And then in the y of t equation, that second spot, we're going to type in our second equation that we found. So that was our y of t equation. So there's our y of t equation. So we're going to type in negative 0.685 cosine of 2 pi t divided by 0.48.
Did you get the T?
It's the same variable you always push.
Did you do it?
Just that.
Okay.
Divided by 0.48 plus 1.015. Same thing over here. All right, are you ready? Are you with me? Yeah, everybody? Getting it typed in there? Okay. All right. So that's entering in the equations. There's a few other little nitpicky things that we want to do. On the Casio, so one thing that we can do is we can actually change the style of the graph in what it's graphing. Normally we graph a line. That's what this little symbol means on your calculators, is that it's graphing a line. And then same thing here on the Casio. These little things here mean it's graphing like a line segment, okay? We want to change that. And so you can move your cursor up to that little symbol and it starts flashing. We want to do the same thing on the Casio. There's not really a good choice there. Oops. That's a good question. Hold on. Oh, I can't remember how to do it with the Casio. Oh. Dang it. Okay. So on this, you just hit enter, and you're gonna hit enter. If you have a newer calculator, it does it a little differently. So, until you get to the ball, you just hit enter. There's the ball option right there. No, hit it one more time. If you have a newer model one, then it does. You have to select it. But did you get it? Yeah. Okay.
I'm not sure.
Yeah, it doesn't work on the Casios very well. So on the Casio, if you just highlight that bar, really highlight that line, I think you can do style. Style is an option there. So style, and then the only thing we really have is just the dots, and so you can change it to sort of a dotted line instead of a solid line. Okay, it doesn't work great. The last thing we need to do is change the window. And so both of ours are going to go to window and Casio viewing window. On the TI, the important things here are right at the beginning. You can see Tmin is supposed to be 0, Tmax is 4.8, and Tstep is 0.05. So put those in. On the Casio, that stuff is towards the bottom. So there's Tmin is 0. Tmax should be 4.8. Where did 4.8 come from?
You said 4.8.
It's written right there. Tmax equals 4.8.
Oh,
What was significant about 4.8 in our story?
It's the second time by
The time for 5 swing cycles. Okay, so this is going to show us 5 swing cycles. And I don't know what this is. I don't know if it needs to be 0.05. I can't remember what I did.
it's
Okay.
T stuff.
All right. And then we need to use the window settings from your data in part A. So we want to set the X-min and X-max based on our graph that we set up in the very beginning, because we want to see the whole motion of the ball, which means that I need my X-axis. How far to the left does my X-axis need to go? Negative 2.26. I'm going to make it just -3. And my X max should be 3. So that'll be fine. So I'm going to do the same thing. Oh, I don't know what that did. Okay, and then, oh, geez, this is weird. Okay, so -3 to 3. Oh, yeah. And then my Y minimum to maximum. The Y minimum we want to be like 0. And the maximum height we get up to is 1.7, so maybe 2 would be fine. So the Y min would be 0 and the Y max would be 2. Okay? And then, okay, TIs, you can hit graph, and Casios, you can do exit and draw.
My thing is that
Oh, what did it do? Oh, it didn't work right.
mine just did this.
Yeah, so it drew it actually. You're seeing it go back and forth. That's right. All right, did you see
I
it?
don't know which buttons. We have mine's on a brown and yours, and I'm like a brown one. Yeah.
Stop doing this.
Can I make it do that?
Yeah, you have to make a change. So like if you change and just overwrite.
That's pretty
Okay, I get to do it off. That's kind of cool, right?
Mine sounds like parabola.
Okay, that's it for today. You guys, I'll come around and help you if you didn't quite get it. I don't know what was wrong with my Casio that didn't work quite right. You guys are going to start working on your little project. This packet is due today, so make sure you finish that up and turn it in. And otherwise, you're starting on your weather project, okay?